This is lesson 13 on the RL circuit, and at the beginning of the last lesson I talked a little bit about this and at least mentioned it. So what we're going to do here, I'm going to explain a few things and there will be some calculations for you to do, but we're not doing an experiment. Part of the reason was, as I mentioned with the capacitor one, you have to have the right combination of inductor and resistor and frequency in order for the oscilloscope to show what you want to show. And it seemed like all the ones that we had didn't really show things the way that I thought they should. So I decided the capacitor, the RC circuit lab was kind of a long one anyway. And this one is analogous to that, except a few things are the opposite. So I thought, well, we don't really need to actually do an experiment with this one. So if you notice, these are pretty much the same pictures that I had before, that if you have an inductor, but let's look over here at the circuit first. If we have a resistor and an inductor in series with an alternating voltage source, then we can connect across the inductor, or we could connect across the resistor for our output voltage. Now, there isn't a nice inductor light bulb experiment or demonstration. We had one for the resistor and capacitor, so you could actually see what was happening. But as far as I know, there's not a nice one that you can actually use to observe a light in a light bulb. Now, what happens, as was explained in lesson 7, when a current is going through a coil, there is a magnetic field produced, and there's a changing magnetic field because as the current tries to build from 0 up to something, the current is changing, the magnetic field is changing, and as a result there is an induced voltage opposite of the one that's there. And the whole idea is from Lenz's law that this inductor does not allow the current to build from 0 to its maximum value instantly. It reacts so that it tries to keep the current from building. Now, it doesn't succeed, but the current then does build from 0 to something instead of getting there instantly. So here I've drawn the graphs, and these are what you can draw on page 103. So they look exactly like we had before, and as the current builds, then the voltage would build across the inductor. Now, if you were to suddenly take out the voltage source, the tricky part is to take out the voltage source and then reconnect up here without there being an actual break in the circuit. And in lesson 7 there was a diagram there where you have to open one, you actually close one switch and then open another switch. So you actually make a connection here and then take the voltage source out. But it has to be done very quickly. So what we're going to look at here is the similarities. The time constant for an RL circuit is L over R. Remember, with the capacitor it was R times C, but here it's the quotient. And you can do the same sort of things if you have the proper time constant or the proper frequency here. And I actually sort of obtained one of these, but it didn't look exactly quite like this, and so I didn't get very good results. But the theory is that the voltage will build as long as the voltage is applied a particular direction, then it will build across the inductor to its maximum value. At one time constant, the voltage will be 0.63 of its maximum value, and then when you take the voltage source out of the circuit, and then the current will die off, and you will end up at 0.37 times the maximum voltage at one time constant. So I have those things here. I also wrote the time constant there. Now the other thing that I wrote here that I didn't write when I was talking about the capacitor one is the reactance is omega times L. And so I thought, since I'm here at the board in this one, I might explain a little bit more, and it will make more sense. You might want to go back and think about the capacitor problem. But the reactance is omega times L. So at higher frequencies, this has a larger reactance. So that means it has more of an effect in the circuit. And you could see why that would be, because it's the changing current that makes the inductor have its effect. So if the current is changing, if it's oscillating back and forth very rapidly, then it's changing a lot. And so when it's changing, it has a larger reactance and it has more an effect in the circuit. So at high frequencies, then this V out is going to be a significant fraction of the input voltage. And at low frequencies, this really acts like just a plain wire. So in that case, it really has very little effect in the circuit. So for the low frequencies, it's not going to have much voltage out, and therefore this would be a high-pass filter, because the high frequencies you will get a result over here. Now, if you're connecting here for high frequencies, and this would be a high-pass filter, then if you were to connect across the resistor instead, that would be a low-pass filter. Now, this, of course, is the opposite effect as with the capacitor. When we had the capacitor here, the capacitor must charge for a while in order to have an effect, so the lower frequencies then are what are going to give you an effect. And so that's another reason that I didn't actually work any harder at finding an inductor and resistor that would work, because once you've figured out the RC circuit, then the RL circuit is almost exactly the same, except that it's the opposite. So if you were measuring V out, whatever effect you had in the capacitor problem, you would have the opposite effect if you were doing this inductor problem. I still have some problems there for you to work, and you should be able to do those fairly easily once you get the capacitor problems figured out from the last lesson. And I think that's all I'm going to say about that one.